3.1.4 Mechanical equilibrium without thermal equilibrium, the absence of convection. In the last example, we were in both mechanical equilibrium, static, V equals 0, and thermal equilibrium, T equals constant. Is mechanical equilibrium possible when not in thermal equilibrium? Fluid motion to equalize temperature is known as convection. So, for equilibrium to be stable, there must be no convection. Consider a specific volume V of P, S at a height Z. Suppose an adiabatic displacement upwards by x is possible with nu V of P', S, where P' is the pressure at height Z plus x. To have stability need, V of P', S' is greater than V of P', S, such that the displaced fluid volume is heavier, thus a restoring force. Since the difference is at fixed pressure and we have the fraction with numerator S' minus S and denominator x vector derivative of S with respect to Z, then
see equation 3-22. Using the thermodynamic relation. See equation 3-23. This becomes see equation 3-24. And since t is greater than 0, c sub p is greater than 0, and partial derivative of v with respect to t sub p is greater than 0 for most substances, water being an exception, we must have see equation 3-25. In order for there to not be convection, let's rewrite in terms of heat temperature gradient.
See equation 3-26. And using derivative of P with respect to Z equals minus G over V. See equation 3-27. Using the compressibility definition beta equals 1 over V times partial derivative of V with respect to T sub P. See equation 3-28. Condition for absence of convection. So for convection to not occur, the temperature must decrease upwards with gradient less than the fraction with numerator G of beta T and denominator C sub P.
3.1.5 Bernoulli. Starting with see equation 3-29. Let's now consider the special case where partial derivative of v with respect to time equals 0. For such there will be streamlines defined by see equation 3-30. Let's take the unit vector of the streamline to be vector L, where we then have vector L dot gradient W equals partial derivative of W with respect to L. Streamlines are parallel to velocity, but v cross gradient cross v must be perpendicular to velocity, thus
see equation 3-31 becomes see equation 3-32. If there is Earth's gravitational field, then see equation 3-33. 3.1.6 Energy flux. Consider the energy of a unit volume of fluid. See equation 3-34. Where there is the usual kinetic term and then an internal energy term with epsilon, the internal energy per unit mass. The change in this energy over time is given by
see equation 3-35. Using the general adiabatic equation, the relation d epsilon equals T ds minus P dv, the equation of continuity, and Euler's equation, we can rewrite. See equation 3-36.
Where V times 1/2 rho V squared plus rho W is the energy flux density vector. Negative the contour integral from 2 of V times 1/2 rho V squared plus rho epsilon dot df is the energy transported. And the contour integral from 2 of PV dot df is the work done by the pressure forces. Note convention that df is a surface area infinitesimal that is directed along the outward normal.
3.1.7 Momentum flux. For the momentum flux we want to consider partial differential rho v divided by partial differential t using tensor component notation. See equation 3-37. Use the equation of continuity. See the next equation. And use Euler's equation. See the next equation. Where Einstein's summation convention on repeated indices is in use, to get. See equation 3-38. Where normal pi sub ik equals p delta sub ik plus rho v sub iv sub k. So,
see equation 3-39. And using df sub k equals n sub k df. See equation 3-40. Where normal pi sub ik is the momentum flux density tensor. 3.1.8 Conservation of circulation. Consider the velocity circulation around a closed contour. See equation 3-41. If we take the time derivative, see equation 3-42, where use is made of Stokes' formula and the fact that the integral of a total derivative along a closed contour is 0. Thus we get
see equation 3-43. This is known as the law of conservation of circulation, aka Kelvin's theorem. Using Stokes' formula, this can be written. See equation 3-44, which shows that the vorticity gradient cross V moves with the fluid. 3.1.9 Potential flow. Consider steady flow with streamline formation as described previously, and recall from the previous section. See equation 3-45.
Where dF is a fluid surface element spanning a closed contour. Consider a closed contour containing a streamline that moves with the streamline. If gradient cross V equals 0 at a point on the streamline, then it will remain so elsewhere on the streamline. Notably, if there is an asymptotic region of the flow with uniform flow, then we have gradient cross V equals 0, thus we would have gradient cross V equals 0 throughout. Such flow is known as potential flow since a vector field having 0 curl, gradient cross V equals 0, can be expressed as the gradient of a scalar.
See equation 3-46. Since gradient cross gradient phi equals 0 is an identity. In practice, the argument that gradient cross V equals 0 along a streamline will fail for the interesting boundary cases of streamlines that run adjacent to a surface. This is because the closed contour construct circling a point on the streamline will not be possible in such cases. It is typical to have gradient cross V is not equal to 0 at surfaces. Moreover, at a surface the no viscosity assumptions will break down the existence of boundary layer effects, so more information about surface behavior must generally be specified.
Away from surfaces, however, we can usually describe flow as potential flow, and substituting the potential form V equals gradient phi involving the scalar field phi into Euler's equation, we get see equation 3-47, and for steady flow, f of t equals constant. This is known as Bernoulli's equation and, given the nature of potential flow, it is valid throughout the fluid, not just comparing on a streamline.
3.1.10 Incompressible fluids and complex functions. Let's now consider incompressible fluids, specifically, and show the relation to complex functions. First, recall the Euler equation with constant density. See equation 3-48. The equation of continuity becomes a vector flow divergence 0 relation, gradient.v equals 0. If compared to the Bernoulli derivation, we see we have W replaced by P divided by ρ. Thus, we have the relation. See equation 3-49.
And also gradient cross V equals 0. Introducing V equals gradient phi as with potential flow, we have see equation 3-50, which is Laplace's equation. We will examine this equation for 3D extensively in later chapters describing electromagnetism. In 2D, due to symmetries or constraints, fluid flow or electrostatics, however, Laplace's equation can be written in terms of a potential function like above and a second potential function related by way of the Cauchy-Riemann relations.
Since we have gradient cross V equals 0, we can write in terms of a potential function phi. See equation 3-51. Thus have see equation 3-52. Since gradient.v equals 0, we can write see equation 3-53. If we introduce a second potential function psi, then the above is satisfied if v sub x equals partial derivative of psi with respect to y and v sub y equals minus partial derivative of psi with respect to x. The potentials are then related according to
see equation 3-54. These are precisely the form of the Cauchy-Riemann relations for a differentiable complex function. See equation 3-55, where z equals x plus iy. See Appendix A for details, as well as Chapter 2. By connecting to complex function theory, any problem can be easily solved, no matter the 2D boundary, by way of the Schwarz-Christoffel transform, see Appendix A, and use of a computer if still needed.